Hello, my name is Roddy Urquhart. I'm Senior Director of Marketing at Codasip, and I'm going to be talking today about the integrated UVM environment for verifying the adding of custom instructions to RISC-V cores. We'll be talking in two main sections. One is talking about the process of RISC-V customization itself using Codasip Studio, and secondly, RISC-V verification using Riviera-PRO. So what are RISC-V custom instructions? Well, the RISC-V open instruction set architecture provides for a base instruction set, a number of standard extensions, but also provides for the user to create their own custom extensions. So why would anyone do that? Well, with a general purpose core, there are sometimes computational bottlenecks, particularly with algorithms for things like DSP, cryptography, or artificial intelligence. So the general approach that we would take is to use software profiling to analyze hotspots, then define and analyze the custom instructions, and when you're satisfied with them, to create and verify the HDK and SDK for the extended core. So why use automated tools as we are advocating? Well, a common approach is to manually add custom ISA extensions. So you have to define the new instructions, then modify both the instruction set simulator and the RTL. You probably have to create intrinsics for your compiler, modify the assembler, add support in the debugger, and verify. All together a challenging, time-consuming, and expensive process. On the other hand, as I hope to show you, if you automatically generate your HDK and SDK using Studio, you reduce the time needed for toolchain and RTL modification, you reduce the cost of custom processor development, and the resulting processor is easily programmable using standard C or C++. So what is Codasip Studio? It's a collection of tools for processor design or for the fast and easy modification of Codasip's RISC-V processors. It's an all-in-one set of tools, highly automated, and has been around since 2014. Processors designed in Studio have been silicon proven by major semiconductor vendors. So the starting point of working with Studio is the CodAL language. The CodAL language is a C-like language which allows both instruction accurate and cycle accurate descriptions to be created in a single CodAL model. These can be provided to our IP customers as a starting point for modifying their processor optimizations and modifications. So if you wanted to modify a Codasip RISC-V core, your starting point would be one of the existing cores, which would be BK3, 5, or 7. You would probably want to add instructions, potentially add some other resources such as registers, and in an extreme case, you might want to modify the pipeline. After this, you'll automatically generate a software design kit consisting of a compiler, assembler, linker, debugger, IDE, etc., and a hardware design kit consisting of RTL models, synthesis scripts, verification models, and virtual prototypes. So how complex is it to extend a RISC-V core? We did an exercise with a single engineer and asked the engineer to take the draft RISC-V-B extension and implement it in the CodAL language. The first stage was to write an instruction-accurate functional model. This took 10 days and resulted in 900 lines of code. Then a software development kit was automatically generated and evaluated. The next stage was the implementation model, which again is written in CodAL. This time it took 3 weeks and 1,500 lines of code, and then from that the hardware design kit could automatically be generated. Now, verification is an essential part, probably the most important part of a processor development cycle. There are two main elements to it. You need functional coverage, so you need a test plan to verify the functional correctness of the design and cover points for each of the functional features, and you're looking to achieve absolutely 100% coverage. Code coverage can be a little more tricky. This assesses how well the code has been exercised, and some parts of the code may be tricky, for example, state machines, but you're still wanting to achieve a high percentage like 90–98% if possible. And you need to compare your RTL against the golden reference model. So this is where processor IP co-verification comes in. Codasip has a strong methodology with a standard approach involving both simulation and static formal analysis. So we use a consistency checker, random assembler program generator, and we automatically generate a UVM environment. This environment is in System Verilog, and you can use Riviera-PRO to check that the synthesizable RTL matches the golden reference model. So we're now going to look at verification of RISC-V using Riviera-PRO. Riviera-PRO has a rich set of features for analyzing the design in an effective debug environment. So if you're verifying the RTL code, there's a robust set of analysis and debug tools. So for example, here we see a waveform viewer, a hierarchy viewer, and a special object viewer for finite state machines. There is also cross-debug with the joint Codasip Aldec solution, allowing you to have full debug simultaneously on both C and RTL code. And for UVM, there is a complete set of tools. There is a UVM graph representation. There is a hierarchy view, and you can look at configurations. So you've got an overall perspective on the testbench architecture and the data flow. As we saw earlier, coverage analysis is an essential part of the process of verification, and Riviera-PRO provides a range of code, FSM, assertion and functional coverage viewers. So summing up, together, Aldec's Riviera-PRO and Codasip Studio provide you with a complete set of tools to modify a RISC-V processor core and to verify it. So in Studio, you can describe the RISC-V architecture and add custom instructions. You can automatically generate the UVM environment and configure random assembler program generation, and you can kick off RTL simulation, set breakpoints, and debug. In Riviera-PRO, you have the ability to run simulation and debug applications. You can expect simulation waveforms and gain an overall perspective on the testbench architecture and the data flow. And all importantly, you have viewers which enable you to check out both functional and code coverage to assess how effective the UVM tests have been for checking the RISC-V design. This demonstration is focusing on Codasip Studio and using it to extend a processor core. Codasip Studio can be used to create processor designs using the CodAL processor description language, and so you can use it, for example, for taking an existing RISC-V designed in CodAL and extending it with custom instructions. For the purposes of this demo, we're going to take a very, very simple processor example called URISC, and we're going to look at a particular simple application, which is a bit count benchmark. So here you see the user interface for Codasip Studio, and on the left in the Project Explorer, you see both the URISC core and the bit count application. So if we take a look at the bit count application, we can bring up the source code, and you can see that there is a function here which implements a parallel shift test, and then there is this function is used in a loop, which is the main code for the benchmark itself. So if we're going to run this code on the URISC, we will need an SDK for the URISC. So on the right, we can go in and generate an SDK. We start with building a simulator, then an assembler, then a disassembler, then a profiler. Then we finally move on to the compiler and libraries. So we'll wait for that to complete. Okay, so now the SDK is ready, and we can compile the bit count application and move on to profiling. So we select the bit count code, we give the profile a name, and we want to choose the simulator. We're going to choose one which is an instruction accurate simulator with profiling enabled. So we want to annotate the sources, annotate the assembly, but we're not interested in the decoded sequences. So we now run the profiler, and the code takes over 22,000 cycles. And now if we look back at the source code, we see in red the hotspots. So we can see that a lot of them are in the bit count function. And then we also see that the loop at the bottom is marked as red. So given that the bit count function is a hotspot, we can look into creating a custom instruction that will accelerate this bit count function. So we go back into the URISC core, and we go to the instruction set architecture, which is described in the CodAL language. So here we see the CodAL source code. So we add an instruction I_bit count. Now we're going to copy some code from existing instructions to make things a little bit easier. So here we're going to add an opcode for bit count. Then put that into the instruction. Now we are going to use a source register, and also we need a destination register. So we're going to rename the instruction. So rename the opcode, and we need, for the assembly level, we need to add the destination register. For the binary, we need to remove some unnecessary code and to add the destination register. Then we move on to the semantics, and as a starting point we can use some of the C code in the bit count example. So we copy that code there. We also need to read the source register. Need to define the word type. And then we need to write the result to the destination register and remove some unnecessary code. Need to fix a few other things in the code here. Just check the semantics. Okay, this seems to be okay. So now we just add in the comment to label the new instruction. So we created a new instruction to address this bottleneck. We now have the issue of compiler hints. We're not going to use the compiler because this is a rather complex instruction. Instead, we're going to use a built-in. And we also need to let the compiler know a define instruction set extension define, so that we can know when to use that when compiling the bit count function. So we want the bit count function to be portable so that it could work on existing cores where it's running, but also run on the modified URISC core where we've added this extra instruction. So summarizing, we've got this new instruction I bit count with destination and source registers. This is reflected in the assembly description with both registers and the opcode, and also in the binary. The remaining bits, that's just padding out so that we've got a 32-bit instruction. We read the register, we've got the computation to generate the result, and we've got these 3 hints for the compiler. So a built-in will be used, and this will be dependent on defining ISE_ext. And finally, we write out the result to the destination register. So we're going to, as the next step, we're going to have to update the source code of the bit count. But before we do that, let's start generating the new SDK for the extended URISC core. So we kick that off, and we start building the different SDK elements, starting with a simulator. Now, meanwhile, we can go back and we can edit the bit count code. So we need to be sure that it's recognized whether the ISE_ext define is there or not. So we add an ifdef statement. So ifdef ISE_extend, else we revert to the original code and it would be executed as done previously. Now, if ISE_ext is defined, we want to add a built-in. Now, we're waiting for the SDK generation to finish, so we need to be a little bit patient. And when that's done, we can take a look at the built-in. Okay, so the SDK is now generated. So let's look into the instruction accurate SDK folders. And there is this header file inlines.h. And here we find the bit count built in. So we need to add this to the C code. So it takes the argument x and generates result n. We also need to make sure that the built-in is included. So we use the definition and we put in an include statement to include the inlines.h file. Okay, so we've now modified the bit count function to take account of the built-in. So we recompile, and now we go back to the profiler and rerun that, getting a new result. So we'll want to compare that with the original. So the original had over 22,000 clock cycles. With the modified extended core, we reduce that to just over 10,000 instructions. So we're talking of a 2x improvement by adding this single instruction to the URISC. So let's see how the profiling looked when the original code is annotated. Here we see that the original hotspot in the parallel shift test is gone, and instead the built-in function has been used because ISE_ext was set, but we still see a hotspot as expected with the main loop of the benchmark. So we've achieved in accelerating that hotspot, and summarizing, we've had a 2x improvement. So we can now move on and generate other things that are relevant for verifying the extended core. There are a number of possibilities here on the right. And the first one we're going to look at is the random assembler program. So let's bring that up. We have a number of parameters we can set. We can control the number of generated programs and the number of instructions. There are further parameters that can be set. So let's generate the 10 random assembler programs. And now take a look. So here we see the 10 programs. And if we look at one of them, you just see that there is a random collection of instructions there, as you'd expect. So that's one thing we can automatically generate from Studio. The next thing we can look at is RTL. So RTL is important because we want a synthesizable version of the extended core. So let's generate the RTL. We also want to have test benches. So that's now built. So if we go into the cycle accurate area of Studio, here we see a bunch of RTL programs which describe the URISC core. In the test bench area, there are a number of test benches that have been generated, including a simple test bench and one using JTAG. If we look at the simple one, you can see that the code is highly readable and well formatted. And these two test benches will be run later using Aldec's Riviera-PRO. The final part is to generate the UVM environment. This contains UVM code and also a golden model against which the synthesizable RTL description of the core will be checked. So that has now been built. So if we go into the UVM folders, we see a nice hierarchy of elements there. And if we look at the top level system Verilog, again, you see it's very well formatted and readable code. So summarizing, we started off with the simple URISC core and a very simple benchmark called bit count. We profiled the bit count benchmark and discovered an area of code which was a computational hotspot. We then created the bit count instruction, which was added to the CodAL for the URISC core. We then regenerated the SDK, ran the profiling, and found that adding this single instruction resulted in a 2x speed up to the bit count code. We've then generated everything that's necessary to verify the cycle accurate RTL. We've created test benches and also a UVM environment, both of which can be shown later using Riviera-PRO. Now, in this demo, we're going to be looking at three things. We're going to look at the simple usurvey test bench. Then we're going to look at debugging using a combination of Studio and Riviera-PRO. And finally, we're going to look at UVM verification. So we'll start with the first and simplest case, which is the test bench. So let's look at the bit count project. As we see, everything is already built, so we can now go and start the Riviera test bench. So next, the Riviera GUI is visible, the project is elaborated, and the test bench is run. And after the simulation has run, we can zoom into the waveform viewer to look at some of the details. And you'll see some of the signals there, JTAG at the top. And here we're looking at the memory interface. And we can look at detailed things like the program counter, where you see various values in the viewer. And we can look at details of resources such as the register file here. So this can be a useful way of looking at the behavior of the RTL, but we may want to see more details, for example, see the JTAG interface being exercised. So that's the next part of the demo. For the second part of the demonstration, we're going to look at interactive debugging. So we choose a debug configuration, which contains the co-simulation between Studio and Riviera. We're going to use the same bit count software example that we had in the test bench. We're going to select OpenOCD and the RTL simulator, and we have a Python script which can be used to run both OpenOCD and Aldec's Riviera-PRO. So if we hit debug, we start up OpenOCD and we start up Riviera, and we can look at the software debug in the normal way. We can step through the code, we can set a breakpoint, and we can inspect variables inspect registers, and we can look at memory. So all the usual things that you'd expect from your software debug. Meanwhile, you can stop the RTL simulation and inspect the waveforms. Then you can resume the RTL simulation and then go back to the debug of the bit count application. So that's showing interactive simulation. The next example that we would like to show is to run a third example, which is the UVM. And in this case, we are verifying the RTL against a golden reference. So here the elaboration process starts, and we now have a fully elaborated UVM. We're adding interesting signals from both the golden reference and from the RTL. And the simulation continues to run. We've now finished the simulation, and we can look at some of the reports that are available in Riviera-PRO. First of all, we look at functional coverage. So we can inspect the register file and see what the cover points there look like and the coverage that's achieved. Then we can look at the memory interface and see if those protocols have been covered. Then we can move on to assertions and look at how often they've been evaluated and whether or not there have been failures during the simulation run. Then we can look at code coverage, and here we're going to create a report in HTML, which we're exporting, and we're now going to go back to Studio, and we're going to drill down into the processor and look at the code coverage. So here we're selecting the fetch unit, and we see that the fetch unit has statement coverage of 100%, there's branch coverage, expression coverage, and condition coverage. So summing up, with this UVM example, we've been able to see that we can verify generated RTL against a golden reference using UVM and Riviera-PRO. So we've seen three examples altogether. One was a test bench. Secondly, we've seen interactive debugging, where we've been able to look at the RTL while continuing to debug our software application. And thirdly, we've been able to look at UVM-based verification of RTL. As I hope has been clear, there is very good integration between Codasip Studio and Riviera-PRO, and together they can be a very effective way of verifying processor cores. Thank you.